For this third computer session, we are going to take a break from generating spatially variant anything and just talk about what is a two-dimensional fast Fourier transform, or more specifically a discrete Fourier transform. How can we visualize that? What does that mean? And how can MATLAB help us investigate that? So that's what we're going to do here. And even if you're not interested in spatially variant lattices and you're here just to get a better, more intuitive feel about what the numbers from an FFT really are, this I think is the computer session for you. So we start our MATLAB as we do all things that I like to do. I like to close all the figure windows that might currently be open. I like to clear the command window, and the most important, clear all the variables from memory. Next, I open up a figure window. In this case, it's taking up the whole screen, and the background color is white. So if we run it, this is what we see and what we get. In the dashboard are all the hard-coded numbers. We don't do any work here. We just define how many points we want on our grid, stuff like that. The rest of the code will then be based on the numbers in the dashboard. So we're going to be calculating a two-dimensional FFT of a small object. We're going to call it our unit cell because we're working with periodic structures. This is a computer session and a series of other things. If you're not following the spatially variant lattice stuff, it's just a small image, a picture, simple picture that we're going to create, FFT it, and figure out what the numbers really mean. So we're going to call this picture our unit cell. We need some parameters. We'll give it a lattice spacing of 1, which means the physical width and height of this object will be 1. And we're going to draw a triangle, and we will make each side of that triangle have a length of 0.9, and 0.9 times a to be more specific. We need a grid to build this thing on. So let's make it 255 points across. And we'll use the same number of points tall. Okay, let's go to the next section. We're going to go back and add more parameters in a bit, but that's a good start. First step in this code is to build our unit cell, or build the picture of the thing that we're going to Fourier transform. So we need the rest of our grid. The cell size is the physical width of our object divided by the number of points we've just defined. The height of the cell is the same thing but divided by ny. Now we're going to create an array of numbers that tells us the position of each point as we work horizontally across the grid. And the same thing working vertically. And I always like to center my grids about 0. So I'll just say xa equals xa minus the average value, and then do the same thing for y. Let's run it, make sure there's no errors. Okay, no errors, so we will keep going. And we'll generate our mesh grid now. Sometimes I end up using the mesh grid parameters, sometimes I don't. It's just a habit to create them, I think. Okay, so we're going to draw a triangle, and we need to calculate the top and the bottom of the triangle in terms of the indices of the grid. So if we have 255 points vertically, maybe it starts on the 100th cell and goes down to the 200th cell. We need to figure out where those are so that it's centered vertically. Calculate the grid indices of the triangle. The physical height of the triangle is the side of one side times the square root of 3 over 2. And I'm not going to work through the geometry of that, but if we have a triangle with all three equal sides of length w, the height of that triangle is this equation, w times the square root of 3 over 2. Next, I'll calculate how many cells tall that triangle will be. Well, it's h over the cell height. Now we want to calculate where we're going to start. What's the first indice of the triangle, the bottom or the top? And we'll calculate it this way. And essentially what we have is big NY divided by 2, so that's the middle of the grid, minus little ny over 2. Of course, rounded to be an integer, and that places us at the top of the triangle. And then the bottom of the triangle is ny1 plus ny minus 1. So that will take us, ny1 to ny2 will take us from the top to the bottom of the triangle. Now we want to build the triangle. We will initialize our unit cell to all zeros, and now we'll set up a loop that goes from ny1 to ny2. What I like to do first is to calculate a parameter that as we go from the top to the bottom of the triangle, or bottom to top, a number that goes from 0 to 1, and that'll let us calculate how wide the triangle needs to be at that point. So we'll use f for that. So in order to start at 0, we will say ny minus ny1. That'll be an integer that starts at 0, and then we will divide it by ny2 minus ny1. That ensures it goes up to a maximum value of 1. Now I actually don't want to start this at 0, because if the width of my triangle is 0, I'm not putting anything on the grid. So what I'll do is add 1 to this, and now we start at something that's just a little bit bigger than 0. And since I add a 1 there, I have to add a 1 in the denominator to make sure we go from like 0.01 or whatever that number might be all the way up to 1. And instead of having a number that goes from 0 to 1, I'd like to go from 1 to 0. So I'll just say 1 minus all of that. So that's f. F will tell us the width of our triangle. So we're going to calculate, as we're going from bottom to top of our triangle, how many cells wide we currently are. And W is the total length of one of the sides. So if we multiply that by f, that will let the width of the triangle go from small to big, or big to small. We divide by dx, and that tells us how many cells wide the triangle is at that particular value of ny. Now we need to figure out where it starts and stops in terms of grid indices. We'll use the same algorithm for centering. Okay, looking good. So now we have all the indices to go ahead and fill in the triangle. So we'll do that now. And we'll go from nx1 all the way over to nx2. And how far up and down are we? We're at ny. We'll stick a 1 in there. At this point, we should have built our triangle. Let's look at it to make sure we have. So we'll open up, we'll make it a subplot. We're going to draw a few things as we go on. So this says it's 2 subplots deep, 3 subplots wide, and we're plotting into the first one. I like to use image SC, so we'll get a handle to image SC when we draw the unit cell. We'll get a handle to it, to the parent, and then we can set the Y direction. If you've watched the other computer sessions we've done, this shouldn't be any surprise to you. Image SC comes off reverse normally to an axis equal tight, color bar, and we'll give it a title. Call it our unit cell. Okay, now if we run this, we should know if we get a triangle. Okay, we get a nice triangle. 1's in the triangle, 0 outside of the triangle. This is the object that we're going to calculate our two-dimensional discrete Fourier transform using the FFT, and then we'll play around with the numbers to figure out what everything is. Alright, next section of the code. Call this compute Fourier expansion. And this is where we'll calculate an FFT, and we will draw it to the screen and try to figure out what's going on. Okay, so we'll let A be the two-dimensional FFT, and MATLAB has a built-in command FFT2, and then we want to show the FFT. So we'll go to the next subplot, and we will just copy and paste the code that we had up there so we don't have to type it all again. Now, this is going to be a complex number, so let's choose to plot the real part of A. And give it a title. This is the FFT2. Okay, we'll let it run it and see what happens. So over here, we're looking at the FFT. To see this a little bit better, what I'm going to do is redraw this, but fill up the figure window with it. A real quick way we can do this is just to follow the subplot with a CLF, clear the figure window, and then we can just delete that in the end. But I want to look at this. Now what's going on? Notice, if you can see it on the video, most of the numbers are crammed off into the corners here. And we were probably expecting the 2D FFT to have all of the big numbers in the middle. And we can do that with the FFT shift command. But straight from the FFT2, all of the numbers that are the most significant numbers are off into the corners. So we want to follow this with an FFT shift. Let's look at it again. Okay. Now it has placed the most significant numbers in the middle of the grid. But there's a problem. Look at the values. We see something on the order of 2 times 10 to the 4th power. That really doesn't make sense. The numbers should not be that big. And it's just a scaling issue with the fast Fourier transform. And if we divide by the number of points, it will fix that. So now we have realistic numbers. Now notice this blue color is essentially 0. Most of the numbers out here are all zeros. But if we zoom in on what's here, the most significant numbers, we see some interesting things happening. It makes sense then that if we want to play with the Fourier transform, we can probably ignore all of what's out here. So the next thing we're going to do is define some kind of window that draws a square in the middle of this, and we'll just pull off the numbers within that window, and we'll call that the truncated Fourier transform, because everything else we're neglecting, it's like we're assuming everything out here is 0. But as we'll see, that's actually a pretty good assumption. So now we'll get rid of this CLF, we'll run it again, and we see our 2D FFT. Not as big, so we can't quite see as much about it, but it is still there. So we're going to pull off a window. We need to know how many of those points we're going to grab. So we'll go up into our dashboard and define that. NP, number of points horizontally. Let's grab 7. NQ, number of points vertically, we'll do another 7. So we're going to grab a 7 by 7 window of points from the middle of that FFT. Now we'll go back down and add the code to do that. Okay, first thing we need to know is where is that 0 order term in our grid. So we run this and we zoom in on it. We have this big number in the middle. What is the grid indice of this, our 0 order mode, or 0 order number? If we were interpreting this as Fourier series coefficients, that would be the DC component. It's the statistical average of all the numbers in the array UC. But turns out, since we chose an odd number for NX and NY, we can figure out where the middle is real easily. It's in the middle of the grid, so if we had 3 points, we would divide by 2, we'd have a number like 1.5, and we round up to 2. In MATLAB, array indices start at 1, so if we had 3 points, 2 would be the middle. So that's the middle horizontally. The middle vertically is ny divided by 2. Next thing I like to do is calculate the left and right, top and bottom edges of this little window that we want to pull out of A. So NP1 will be the first point horizontally, and it'll be the index of where that zero order mode is, minus NP divided by 2, rounding down from that. Then the end point of the window is P0 plus floor of NP over 2. Then I can do the same thing for Q. These will be the top and bottom of that window. Instead of NP, we have NQ. So those are our indices of the numbers to pull out. So we'll calculate an AT. This is A truncated. And we simply go into A and we pull off from NP1 to NP2 and Q1 to NQ2. We've pulled off a little window from A. And we probably want to show that. So let's say show truncated FFT. And we'll put in an AT instead of A. Truncated FFT. And we'll go to the next subplot, 2, 3, 3. Let's run it and see what happens. One thing we need to worry about before we can plot it. This is only 7 by 7. We can't give it XA and Y anymore. So we have to calculate axes for our truncated Fourier transform. Axes for AT. So the p-axis will simply go from minus half of NP over 2 up to positive NP over 2. And we'll do the same thing for Q. And now in this image SC, we have PA and QA. Now we can run it and that should work. Yes. So notice, if I can try to reproduce it over here, we've pulled off a window that is 7 by 7 from our FFT. So I closed in a little bit too much, but you get the point. This is a little window from our original FFT, and the axes now show our coefficient indices, if you will. So here's our 0, 0. This would be a 0 and a -1 for the P index. So we'll zoom back out. Okay, so all we've done now is Fourier transform. What we want to do is interpret what really are these numbers telling us. What is that? And what we'll see is it's actually a planar grading. And behind each one of these, we can calculate a planar grading over top of this unit cell. We can calculate each one, and if we added them all up, we'd get our triangle back. Now, since we've truncated our Fourier transform, we are ignoring some numbers. We're probably going to get a distorted triangle back. And the more terms we retain in the truncated Fourier transform, the better the triangle will look. But in doing this, we'll get very intuitive about what all this means. So let's go to our next section. And what we're going to do is the world's most inefficient inverse Fourier transform. So rather than just do an inverse FFT2, which we could do, and we will do it very quickly, but instead we're going to calculate each of those planar gradings. We're going to draw them. We're going to draw each one, and we're going to add them all up and plot the sum, and we should get our triangle back. So we're reconstructing our unit cell. First, let's do it the quick way, actually using the FFT. So what we'll do is we'll create A again, but all zeros. Remember, this was the full FFT, but what we're doing now is making it all zeros Then what we want to do, we want to fill in where that window was. And we'll put our truncated Fourier transform in there. So essentially it's the original A, but everything outside this window we grabbed is now set to 0. Let's look at that. We'll borrow that code. Actually, let's borrow this. And we'll plot it to 2, 3, 4, we'll plot it to 5. This is just temporary. And let's look at what happened. Notice we've taken what's here and put it in the middle, but everything else is 0. You can see some other non-zero numbers kind of running out in this star pattern that aren't here. It's all zeros except this little 7 by 7 window in the middle. And so up here, if we were to inverse FFT that, we would get our triangle back exactly. But now if we inverse FFT, we're going to get something back that is not necessarily the triangle. Let's see what it is. So unit cell with a T on the end from the truncated data. We will inverse FFT2, our A. However, remember, we did an FFT2 on our unit cell and got A, and then did an FFT shift on it. So we need to undo that FFT shift before we inverse FFT it. At this point, there will also be, maybe, just due to numerical noise, some small imaginary components. So I like to take the real part of that. And also, if you remember the scaling, we had divided by the number of points in the grid, nx times ny. So to undo that scaling, we need to multiply by the number of points in the grid. So at this point, this will reconstruct our unit cell, if you will, but from the truncated set, and it'll be interesting to see what happens. So let's plot the 2, 3, 4. UCT. Okay, so that'll show our unit cell in the bottom left image. The unit cell reconstructed from our truncated Fourier transform. Unless, yeah, of course, we made a mistake somewhere. Oh, I said IFF shift. It's IFFT shift. There we go. And we got this blurry, distorted, bumpy kind of triangle. And that is a consequence of only using 7 by 7 terms from our FFT. Let's use even fewer and see what happens. Let's use 3 by 3. Very small window. And that's barely a triangle. Go up to 5 by 5. Starting to look a little bit more like a triangle, but very rounded. Anyway, the more terms you include, the sharper it looks. Let's go up to 11 by 11. Looking very much like a triangle now, but with a little rounding on the edges. Just for fun, let's go up to 21 by 21. And looking pretty sharp. But we can see some ringing, we can see some craziness happening at the edges. That's Gibbs phenomenon. Anytime there's a step discontinuity and we're using a Fourier transform, we get small spikes in the numbers here, and that's called Gibbs phenomenon. Okay, now what we want to do is the same thing. We want to reconstruct our unit cell, but we want to do it a much more brute force way that will let us understand better, really, what those terms in the FFT mean. There are actually planar gratings, the spatial harmonics, if you will. Okay. save that, but we're going to do something a little bit different. Yeah, we can always copy paste it. Okay, now we're going to do the inverse FFT the slow way. And what we'll do is we'll individually calculate the planar gratings, we'll display them so we can see them, and then add them up and show that we get our triangle back. So we'll set up another UCT. You know what? Changed my mind. Let's store this one that we reconstructed the quick way and display it into 2, 3, 3. So let's run it and see what we're going to have. And so we see the original unit cell, our Fourier transform, and our truncated unit cell. And this is reconstructed the quick way. So when we do it the slow way, we should end up with something that looks the same. Before we do that, let's go back to just 7 by 7. That way we have something that looks a little bit distorted. Make it more interesting. Okay, so here's where we are. So we're going to reconstruct the slow way. We'll display all that stuff along this bottom row, and we'll put our overall lattice as we're adding these planar gratings over here. And in the end, it should look exactly like this truncated unit cell. Let's go ahead and see what happens. Okay. The slow way. So we will initialize another truncated unit cell. We'll start it off as all zeros. Since we're adding all of the planar gratings together, we'll start off with just all zeros. Now we need to set up a loop and loop through each one of those Fourier coefficients in that window that we chose. So we'll say 4NQ is 1 to big NQ. 4NP is 1 to big NP. So this will loop over that little window of the truncated Fourier transform. The first thing we'll want to do is calculate the planar grating. Now, to calculate the planar grating, we're essentially going to calculate this with cosine k dot r. We need the grating vector associated with each one of those terms in our truncated Fourier transform. So in fact, we'll go back a little bit and do that. We'll go right under where we calculated the PA and QA. And we'll say calculate grating vector expansion. And Kx, it turns out the x component of our grating vector is 2 times pi times PA over A. And we'll do the same thing for y, but we're going to use the integers QA instead of PA. And then we're going to mesh grid them. And why are we mesh gridding them? Because at this point at lines 87 and 88, they're just one-dimensional arrays. We mesh grid them and we distribute them out over this window of our truncated Fourier transform. Okay, so now we have Kx and Ky. We can come back down here and calculate our planar grating. And rather than cosine k dot r, what we've essentially done with the FFT is expand our original object into a two-dimensional complex Fourier series. So each term in the complex Fourier series is not calculated with a cosine, but with a complex exponential. And then inside the parentheses I'm working in now, here's where we put the k dot r. So k dot r is kx times x plus ky times y. So what is kx? We're storing a whole bunch of kx's in big Kx, but we're at position np, nq. So that'll give us the kx component of our grating vector that corresponds to the np, nq coefficient in our Fourier transform. So that times x. X is our mesh grid term. And then ky times y. That gives us our planar grating. Let's plot the planar grating. And get rid of that code. We don't need to see the truncated. Okay, show planar grading. And we'll use the p-color command for this. And the reason I deleted what was above there, we're going to plot it into the same subplot. I guess I didn't have to do that. Would have just done it over top. But sorry for that pause. Had a phone call. So we are in the middle of plotting a planar grating. I like to use ImageSC in place of p-color because I feel like it's a more intimate connection to the data. But we have to do some funny things because it draws things inverted. So ImageSC, and we'll look at the real part of our grading because it's a complex number because we're essentially reconstructing a complex Fourier series. We will get the parent to that image. And then we will set the y direction to normal because ImageSC by default is reversed. Axis equal tight to make sure we have the correct proportion. We'll give it a color bar so we know what color corresponds to what value. And we'll give it a title. And we probably want to display the indices of the specific Fourier coefficient we're looking at. So let's do that. We'll say P is num to string PANP. That'll tell us. So P, let's say if we have 7 coefficients going horizontally, this big P will go from -3 up to +3. Go to the next line because I'm running out of room. Num to string QA and Q. And that should do it. That'll give us a title. Let's go ahead and run it and see what happens. And notice nothing is happening. And that is because we forgot to put a draw now in here. MATLAB is relatively smart, and if you're doing a bunch of graphics calls inside of a loop, it must think to itself, whoa, this person wants to run really fast, so I won't display the graphics. So we need to force the MATLAB to draw the graphics. With a draw now. Okay, now if we run it, this will probably go fast. But we can see it iterating through all of the different Fourier coefficients, and each one is a planar grating. Now, it's still not exactly clear what's what. So what I would like to do over in this lower left is draw the truncated Fourier transform, the coefficients, and highlight which of those coefficients is corresponding to this planar grating. So let's go ahead and do that. Okay, so we'll put it in the subplot 2, 3, 4, so it shows up in that lower left. And we'll copy and paste all the ImageSC stuff. And remember we put our truncated Fourier transform inside of AT. And we'll give it a title. Truncated FFT2. Now all this is going to do is draw the truncated Fourier transform. Let's run it, make sure there's no errors. What I'd like to do is highlight whichever cell in here it corresponds to the planar grating that we see over here. So I hit Control C, that's what the error was. So we'll say hold on and hold off. If we were to draw a little rectangle around the Fourier coefficient, the plot might or might not disappear. Some commands erase what's behind it, some don't, and I don't have them memorized which do and which don't. So just by default, I'll say hold on and hold off so I don't overwrite what's behind it. So what we need to do is create an array, and we'll create an array X. This will be the X position of all the vertices working around a square that will highlight our Fourier coefficient. So we have a grid indice, PA, NP, that will be the center of the square horizontally. So the left edge is subtracting 0.5. And then we'll add to it 0, 1, 1, 0, 0. And that's walking around the perimeter of the box, all the X positions. We'll do the same thing for Y. And then we'll use a line. X, Y, and we'll make it black so it stands out. And let's give it a thick line width. Okay, now let's look at it. Now we should see a black box around the Fourier coefficient, and then the planar grading to the right is the one that corresponds to that. And I'm not seeing that, and I know why, because we did not put our Fourier indices here correctly, though, the PA and QA. Yeah, remember this should be PA and QA. Now everything should work. Okay, and notice this black box, the one that it's currently around, this planar grading corresponds to. And what you'll notice is the farther towards the edges, the more periods the grading. We'd call it a higher frequency grading, if you will. Okay, let's run this one more time. So when we calculate the FFT of an object or an image, each one of those terms actually corresponds to a planar grading. Now, if we could take these planar gradings and print them out onto, let's say, a little transparent film, we could actually put all those little transparent films on top of each other, and if we look through them all, we would see our unit cell. So the next thing we have to do then is take each of these planar gradings and keep adding them together and see the overall lattice that we construct, and we'll plot the overall lattice over here. Shouldn't call it a lattice yet since it's only a unit cell. Sorry for misspeaking. So our truncated unit cell is the previous truncated unit cell plus the grading. Now we need to add one thing. We calculated our grading vectors analytically. That's the kx and ky up here. But what do we do with the coefficients? The coefficients from the Fourier transform are what weights the grading. We could either choose to multiply it here or down here. I'll choose to multiply it here. So we need to pull off the NP, NQ coefficient from the truncated Fourier transform. That weights our planar grading because all of them are not of equal weight. That's the meaning of the numbers in the FFT. And this should now reconstruct our original unit cell. Will it do that? Let's see, but we'll have to display it. This is show reconstructed unit cell. Go to the last subplot, so that'll be on the lower left. And we want to plot our UCT. That's the unit cell truncated. And we'll name it reconstructed unit cell. Okay, now this won't quite work. Let's look at it and see what happens. And then we'll fix it. So remember, over here on the lower right, this is our running sum as we're adding all of the planar gradings. It'll look real good once it passes through the zero order. It gets a little bit better. Notice what's happening. That triangle is forming off into the corners, kind of like there's an FFT shift happening. And in fact, that's exactly what happens when we cheated and did it real quick, actually using the inverse FFT. We included the inverse FFT shift. Well, since we're calculating this by brute force, we still have to do that. So we need to incorporate an FFT shift in there. And so the most convenient place to do it, I think, is where we're reconstructing it. So put a reel around it, and outside this, we'll do an I FFT shift. And now when we run it, we should see it create the triangle in the middle. We'll do one thing before we end this, and we'll use a lot of points over here and just let it run and see what happens. It should make a better triangle. In fact, before we do that, why don't we use fewer points? Let's do 3 by 3. And one good thing is happening. Notice the truncated unit cell on the upper right matches exactly the reconstructed unit cell in the lower right. So what we've done is an inverse FFT, a two-dimensional inverse FFT, a very brute force, inefficient way. If you were just going to calculate an inverse FFT, this is not the way to do it. But what we'll see when we're spatially varying gratings, we will decompose a unit cell. When we're spatially varying lattices, we will decompose a unit cell into a whole set of planar gratings doing exactly this. We spatially vary each one of those individually, and we get an overall lattice when we add them up. So let's crank this up to 21 by 21 points and let it run. And what we'll see is that we get a very good triangle. But notice the lower middle figure. When we're looking at coefficients that are near the edge of the grid, it's a very, very high frequency grading. There's a lot of periods within the space of one unit cell. Now the closer that little box in the lower right gets to the middle here, the longer the period grading will be. And if we look at the lower right, it looks like nothing useful is happening, and we might be scared and terminate our program thinking something's wrong, but we just have to let it go. It will eventually fix itself. It'll start to look pretty good once that box passes the zero order mode right here in the middle. Looking even better. This is taking a while. But there is a lesson to be learned here. When we get to where we're spatially varying lattices, we can get our unit cells to look really good, but it takes longer to process all of the planar gratings because we have to spatially vary each one of those independently. And there's tricks we'll get to in later computer sessions of how we can minimize the number of planar gratings that we have to process. Well, we can definitely tell we're getting a nice sharp triangle. We're only halfway done. So once this finishes, that will be it for this computer session. And we're almost done here. And hopefully we get an exact replica. Those two images on the right should be exactly the same. And it looks like they are. So that is it for this lecture.